Hi, my name is MOHAMAD bin SUKHARI. This is our video assignment for MAT222, which is Math Logic. We are from RCDCS1433B, and let's proceed.
That notion here at night when you're home alone. All this shit in my head, yeah, you don't wanna know. On your knees, begging for your life. I'm a 44 till you don't. Now you're gone, knife cutting straight to the fucking bone. Hands full of pills, don't know what the fuck they for.
Hi, my name is IKMAL, and for this video we will cover 3 subtopics for chapter 2, which is truth table, laws of logic and rules of inference. So let's go. Okay, let's get going in the first subtopic in chapter 2, which is truth table. What is truth table used for? Truth table is used to display the relationship between the truth value of proposition. And truth table also can be used in different situations, such as truth table for negation, truth table for conjunction, truth table for disjunction, truth table for implication, and truth table for biconditional statement. Truth table for negation, when the P hold the value true and false, and negation P hold the value false and true. Truth table for conjunction, that P and Q be proposition. The proposition is true when both P and Q are true and false. Otherwise, P and Q is called the conjunction of P and Q. When the P hold the value true, true, false, false, and Q hold the value true, false, false, and the P and Q hold the value true, false, false, false. Truth table for disjunction. Let P and Q be proposition. The proposition P or Q is the proposition that is false when both P and Q are false and true. Otherwise, P or Q is called the disjunction of P and Q when P hold the value true, true, false, false, and Q hold the value true, false, and P or Q hold the value false, true, true, true. Truth table for implication. Let P and Q be proposition. The implication P implies Q is the proposition that is false when P is true and Q is false and true. Otherwise, P is called the hypothesis and Q is called the conclusion when P hold the value true, true, false, false, and Q hold the value true, false, and P implies Q hold the value true, false, true, true. Truth table for biconditional statement. Let P and Q be proposition. The biconditional statement P equal to Q is the proposition that is true when P and Q have the same truth value and false value. When P hold the value true, true, false, false, and Q hold the value true, false, and P equal to Q hold the value true, false, true. Okay, let's have a look for some example. The example says that P equal to Q has the same truth value as P implies Q and Q implies P. P hold the value true, true, false, false, and Q hold the value true, false, and P equal to Q, which will become true, false, true, and P implies Q will become true, false, true, and Q implies P will become true, false, true, and last P implies Q and Q implies P eventually will become true, false, true. This show that P equal to Q has the same truth value as P implies Q and Q implies P.
Next, laws of logic. In this subtopic, we have 12 laws, and the laws are double negation law, De Morgan's law, commutative law, associative law, distributive law, and the Pointer law. And we continue with the next slide. Then, inverse law, identity law, domination law, definition of implication, definition of biconditional, and the last law is absorption law. Proceed to the example. Now I'm going to give some example for laws of logic. And the first example, it states that simplify the following expression: P if and only if Q, and P implies Q or Q. And the first step of the solution, we use definition of biconditional. We change P if and only if Q to P implies Q and Q implies P, and the rest we will just rewrite it again, which is P implies Q or Q. Next, we will use commutative law. We change P implies Q and Q implies P position to Q implies P and P implies Q, and P implies Q or Q. And the third step, we will use associative law. As you can see, I already changed the open square bracket position. And the fourth step, we will simplify it by using the absorption law. And the final step of this example, we will use definition of biconditional. For example 2, it states that simplify by using the laws of logic for negation P or negation P and Q. In the first step of the solution, we use distributive law. Since we can see the P is alone, and we can distribute it inside negation P and Q. Next, we get combination law, because from the first step of the solution, we can see there is P or negation P. We can change it to tautology. And the third step, we will use distributive law, because we can distribute T tautology inside P or Q bracket. Then we will use identity law for the fourth step, which is negation P or Q. The last step is De Morgan's law. We multiply negation inside the bracket, and we get negation P and negation Q.
Okay, now let's go through rule of inference. What is the rule of inference? It is a logical principle or pattern used to derive a conclusion from one or more premises in a formal system of reasoning. These rules serve as the foundation for constructing valid argument, ensuring that if the premises are true, the conclusion must also be true. In this subtopic, we have 11 rules of inference. Number 1, modus ponens. Number 2, law of syllogism. Number 3, modus tollens. Number 4, rule of conjunction. Number 5, rule of disjunctive syllogism. Number 6, rule of conjunctive simplification. Number 7, rule of disjunctive amplification. Number 8, rule of contradiction. Number 9, rule of resolution. Number 10, rule of constructive dilemmas. And lastly, rule of proof by case. Now let's move on to example. If Amin is wealthy, then he is busy. If Amin is busy, then his wife will be unhappy. Amin donate his money, or his wife will be happy. Amin does not donate his money, or he marries another woman. Amin does not marry another woman. Therefore, he is not wealthy. So, for question 1, we must declare the primitive proposition above using symbol P, Q, R, S, and T. So, the solution is P equal to Amin is wealthy, Q equal to Amin is busy, R equal to Amin's wife will be happy, S equal to Amin donate his money, and lastly, T equal to Amin marries another woman. So for question 2, we must write the premise of the argument using those symbols. So the premise that we get is P implies Q, Q implies negation R, S or R, negation S or T, and negation T. So the conclusion that we get is negation P. Okay, for question 3, we need to prove the validity of the argument by using the rule of inference. So number 1 to 5, we substitute the premise that we got from question 2 and we continue with number 6. We get P implies negation R. From number 1 and 2, we use law of syllogism. Number 7, we get R or S. From number 3, we use commutative law. Number 8, we get negation R implies S. From number 7, we use definition of implication. Number 9, we get P implies S. From number 6 and 8, we use law of syllogism. Number 10, we get S implies T. From number 4, we use definition of implication. Number 11, we get P implies T. From number 9 and 10, we use law of syllogism. And lastly, number 12, we get negation P. From number 5 and 11, we use modus tollens. So, the argument is proof. So, the conclusion that we can make for this chapter is argument can be proved by using truth table, law of logic, and rule of inference. From truth tables, it provides a clear method for evaluating the truth of logical statements. From law of logic, we can simplify and validate expression, ensuring consistency in argument. From rule of inference, it helps us derive valid conclusion from given premise. So, together, these tools form the foundation for analyzing and constructing sound logical arguments.
Now we have reached the second part of this video. My name is AFIFI and this is topic 3, proving techniques. Now, a brief introduction about this topic is that we will learn how to prove a statement that we assume to be true. In this video, we will be discussing only 2 proving techniques, which is the first one, forward-backward method, and the second one is mathematical induction. Now, for the forward-backward method, there are 3 simple steps that we can do. The first one is to identify the hypothesis and the conclusion. Hypothesis is the statement that we assume to be true, whereas conclusion is the endpoint from the hypothesis that we need to prove. The second step is to use backward method. Since B is conclusion, we need to derive B1 from that in order for us to make it easier to reach the conclusion when we do our forward method later. Now comes the third step, which is using forward method. Our forward method will start with A1 up until we reach the number of A is logically equivalent to B1. Okay, let's take a look at our first example here. We have if n is an even integer, then n squared is an even integer. Now from the question, we see that it is in the form of implication. So our hypothesis will be n is an even integer and our conclusion will be n squared is an even integer. Now write that down as A and B. Okay, next is we will do our backward method. So B1 will be n squared is equals to 2k. Why is it so? When we take a look at the definition for even integer is n is even if and only if n is equals to 2k for some integer k. So what does this mean is that our n squared is an even integer, so n squared is equals to 2k. K must be an element of integer number. Now, our next step is to start doing the forward method. Okay, so our A1 will be n is equals to 2a. The same reason is because n is also an even integer, but instead of 2k, in here we write it as 2a because k had already represented n squared. we want N here. So just take another alphabet that is not K. So that's why we chose 2A. A also must be an element of integer. Now the next step, our A2 will be N squared is equals to 2A squared. We square the both sides so that we will get our outcome, our direction for this question, which is our B1. So that's why we squared it. Now let's expand and factorize it, and lastly we will get 2 times 2A squared. After that, we will let B is equals to, we will let B as 2A squared. Why? Because on the next step, our A3, our N squared will be equals to 2B. B is an element of integer. And when we take a look back at our A3 and B1, we compare it, it's the same thing. So that's how we know that A3 is logically equivalent to B1. That's it, we have finished our analysis of proof. Now, for the condensed proof, it's simple actually. We just need to write our thoughts earlier. So like I did here, from the hypothesis, N is an even integer, and so on. So it's just like analysis of proof but in sentences. That's all for example 1. Now let's take a look at example 2 next. Alright, so for example 2, we have if S is an even integer and T is an odd integer, then ST squared is an even integer. Now, our hypothesis will be S is an even integer and T is an odd integer. And our conclusion will be ST squared is an even integer. Okay, let's start with backward method. And our B1 will be ST squared equals to 2K. K is an element of integer. We already knew that ST squared is an even integer. So the definition for even integer is equals to 2K. Okay, now let's take a look at our forward method. Okay, our forward method will start with A1. So A1, S is equals to 2A. A is an element of integer. This is because S is an even integer, like it said in A. So that's why 2A. And our T will be 2B plus 1. This is because when looking at the definition for odd integer, it's kind of like the same as even integer, but only plus 1. So that's why it became 2B plus 1. Bear in mind that both of these A and B must be an element of integer. Now, for our next step, A2 will be ST squared is equals to 2A times 2B plus 1 squared. So this is because ST squared, we took ST squared because it is from B1, okay? It is from B1, so we want our A forward method to be in the direction of B1. So that's why we did ST squared. And our 2A times 2B plus 1 is actually we substitute the value for S and T from A1. So that's why we came 2A times 2B plus 1 squared. Okay, so after that we expand the equation and we will get 16A squared B squared plus 16A squared B plus 4A squared. And after that we will actually gonna factorize it, bring out the 2 from the equation, and we will get 2 times 8A squared B squared plus 8A squared plus B 2 times 8A squared B squared plus 8A squared B plus 2A squared. So this is because we want it to get the same result as B1. So B1 here we have 2k, right? So that's why we bring out 2 from the equation of A2. And after that, after we have done bringing out the 2, we will let U for a squared b squared plus a squared b plus 2a squared. And our A3 will be st squared is equals to U. U must be an element of integer. And after that, we will compare A3 with B1, and it is the same. So we will get A3 is logically equivalent to B1.
So now we are moving to mathematical induction. Mathematical induction is used when B has the form for every integer n is greater than or equal to 1. Something happens where something happens is a statement that depends on the integer n. We use mathematical induction because it is not practical to prove the Pn by checking the integer one by one. So there are 3 steps in mathematical inductions. The first step is verify that P1 is true. Replace n everywhere in Pn by 1. The second step is assume that Pn is true. And the third step is prove that Pn plus 1 is true. Start by writing Pn plus 1 and then rewrite Pn plus 1 in terms of Pn. And now we are moving to example question for mathematical induction. So the question is prove that 1 cube plus 2 cube plus 3 cube plus and so on plus n cube equal to n square multiplied by n plus 1 square over 4. So we let Pn equal to the summation of k cube equal to n square multiplied by n plus 1 square over 4. So the first step is show that P1 is true. So we need to substitute 1 into the n. So for our left hand side, you substitute 1 into the k to get 1 cube which is equal to 1. And for our right hand side, you substitute the 1 into the n to get 1 square multiplied by 1 plus 1 square over 4 which is equal to 1. So our left hand side and our right hand side is equal. Thus P1 is true. The second step is assume that Pn is true. So we let Pn equal to the summation of k cube equal to n square multiplied by n plus 1 square over 4. So the third step is show that Pn plus 1 is true. So for our right hand side, we need to find the Pn plus 1. So we substitute n plus 1 into the n to get n plus 1 square multiplied by n plus 1 square over 4. So we simplify the equation to get n plus 1 square multiplied by n plus 2 square over 4. And for our left hand side, we need to find Pn plus n plus 1. So we get n square multiplied by n plus 1 square over 4 plus n plus 1 cube. And then we can get n square multiplied by n plus 1 square plus 4 multiplied by n plus 1 cube over 4. Next we get n plus 1 square multiplied by n square plus 4 multiplied by n plus 1 over 4. And then we simplify the equation to get our final answer, which is n plus 1 square multiplied by n plus 2 square over 4. So our right hand side is equal to our left hand side. Thus Pn plus 1 is true. And finally we have the conclusion for chapter 3. So proving techniques are methods used to establish the truth of mathematical statements. Different types of statements require different approaches and proving techniques. Such as mathematical induction is used for statements involving natural numbers or sequences. And forward-backward method is the basic foundation for all the proving techniques.